AI boom is defined by building capacity in data centers for training large language models. Current application is more you use a web interface, you do ChatGPT and use the large language model. What is still to come is edge AI. I mean, you put a AI chip on a smartphone, take the latest iPhone, and then you can do inference on the AI models right on your end device. You don't need to transfer data like crazy up and down the cloud.
What does the future hold for business? Ask 9 experts and get 10 answers. Bull market, bear market, rates rising or falling, inflation going up or down. Can somebody please invent a crystal ball? Until then, over 40,000 enterprises have future-proofed their business with NetSuite by Oracle, the #1 cloud ERP, bringing accounting, financial management, inventory, HR into one fluid platform. With one unified business management suite, there's one source of truth, giving you the visibility and control you need to make quick decisions. With real-time insights and forecasting, you're peering into the future with actionable data. If I were a larger organization, this is the product I'd use. Whether your company is earning millions or even hundreds of millions, NetSuite helps you respond to immediate challenges and seize your biggest opportunities. Speaking of opportunities, download the CFO's Guide to AI and Machine Learning at netsuite.com/ionai. That's NetSuite, netsuite.com/ionai, EYEONAI, all run together, to get the CFO's Guide to AI and Machine Learning. The guide is free to you at netsuite.com/ionai, netsuite.com/ionai. I generally start by having you introduce yourself and how you became CEO of the electronics business of Merck KGaA in Darmstadt, Germany. And then we'll talk about material science and semiconductors and all of the businesses that you have that impact artificial intelligence.
Yeah, Greg, thanks a lot for having me on the podcast. So my name is Kai Beckmann. So I started in our company already more than 35 years ago. I'm a computer scientist by training. I did a minor on microelectronics, so the kind of the interest for semiconductors is kind of deeply rooted in myself. I then had opportunities to work in all areas of our company. In IT, I was leading HR. I was in the countries running our businesses in Singapore and Malaysia, healthcare business, life science business, performance material business. And then I entered the executive board meanwhile 13 years ago, and being in charge of a number of what we call group functions, HR, procurement, our major production side, our headquarters side, as well as many other functions. And then 7 years ago, I was asked to take over performance materials business, which we have then rebranded a while ago as electronics, based on our kind of transformation away from a materials business to an integrated solution provider for the electronics industry and specifically for the semiconductor industry.
Can I just say, just for listeners who might be confused, Merck KGaA is a German company. It was founded by Jacob Merck, I think, in the late 17th centuries, or Friedrich Jacob Merck. And that company then split eventually between the Merck that Americans know, which is the big pharmaceuticals company, and your company. So they're two separate companies. I think Americans can easily get confused by that.
Absolutely, and thanks for explaining that. So we have a more than 350 years history as the kind of Germany headquartered company, and so we operate in three different businesses. We operate in healthcare, we operate in life sciences, as well as in electronics, so covering a broad spectrum of different industries and different technologies and science.
Can you tell me about the work that you do that is foundational to semiconductors?
Yeah, as I said, our roots are in chemistry, our roots are in biology, our roots are in physics, and if you find physics and chemistry, then you easily kind of reach the field of materials, specialty materials for the electronics industry. And since we started the transformation towards electronics, we combine different parts into our portfolio, different parts across different technology steps, manufacturing steps of making a semiconductors, from delivery systems in a subfab that make chemistry gases available to the tools, to materials across the full production cycle of semiconductors, from patterning to cleans, to planarization, thin film materials, specialty gases. And so we offer a full spectrum, including with the latest acquisition of Unity SC, including metrology instruments for heterogeneous integration, which is a very important kind of new technology required to enhance the performance and the capability of semiconductors.
In the semiconductor manufacturing process, can you is that too complicated to walk us through and tell us where in the process these Merck products come into play?
Yeah, that's a great point. So typically you start with like a blank wafer. A wafer doesn't come from us. So there are other companies who supply the silicon wafer, and then you start processing the wafer. So you start kind of patterning structures on a wafer. This is a lithography step. I mean, you use light in today's world, extreme ultraviolet light to create in a photolithography step structures. Then with that, kind of you wash off the unexposed parts of that. You then build structures on that with thin film deposition on a wafer, and you start planarizing structures in order to get an even surface. You deposit materials to get kind of charged areas on a device, positively or negatively, and then with that you build these semiconductor transistors on a chip. And with that, then with these steps, more than 1,000, meanwhile, in most advanced technologies, more than 1,000 steps, you build these enormously complex devices that can probably host more than 100 billion transistors on one chip in structure sizes that go well down to 2 nanometers scale. And that's kind of a technology which has advanced over the past years dramatically in a way. The level of complexity, the level of performance that has been accomplished, and you need specialty materials to create these highly complex and differentiated devices. That's the way. If you want a kind of a pretty kind of visual number. So if you take our materials and our technologies, our equipment and our instruments, so and if you try to identify in a normal retail store, electronic devices in a retail store, whether they have been exposed to our equipment or materials, there's a greater than 99% probability that any electronic device, TV, handphone, computer, cars, what have you, has been made with the help of our materials, tools, and equipment.
And in terms of materials, those are layers on the the silicon substrate that you're building up as you create the. What's the most common of those materials, or the most heavily used?
When I started doing that at university, and you had a handful of materials that you could use to make a semiconductor. And of course, silicon is the base material, and you have created silicon oxide layers for insulation. You have used aluminum for conducting layers, and that's basically kind of the set of materials. And you needed a couple of solvents to wash stuff off the surface, and that's about it. Meanwhile, we use 80% of the non-radioactive periodic table of elements to make semiconductors. 80%. There's not much left, Craig, on let's say advancing technology. There's a famous quote that was used publicly in many instances by Pat Gelsinger, CEO of Intel, who said, "We're not going to stop innovating semiconductors until we have exploited the full periodic table of elements." This is music to my team's ears. So, of course, for our chemists, that is like the message that drives them to the next level of excitement and performance. And this is what like feeds their brain for making better semiconductors tomorrow.
And who are your principal clients in the semiconductor industry? Is it obviously TSMC or are they component suppliers to the big foundries?
So everyone who makes a semiconductor is on our client list. So we have done kind of a precise analysis. We took the top 100 companies who make semiconductors, and each one of them is on our client list, each one of them. And of course, typically these are companies who have fabs, so not the fabless companies. Of course, they give their kind of manufacturing to foundries, companies who operate fabs. In some instances, the tool companies can be customers too, so they offer then fully packaged solutions to our fab customers. But mainly, it is the semiconductor industry, which is on our client list.
Yeah, and I have to ask. I'm spent a lot of my life in China, so I follow the China story. Are you guys restricted under the export controls to sell to China, or do your materials fall outside of that?
Well, certainly we are restricted, and we follow those restrictions very tightly and clearly. So we operate under all these kind of global rules and special national rules. I think we have to, of course, understand we serve the display market as well, and 70% of the global display real estate, so all display surface, is produced in China, 70%. And so there is almost 70% of smartphones, TVs, automotive displays, they all come from China. So this is, of course, the lion's share of our activities in China, for China.
Yeah. And in the business generally, is it the display business or the semiconductor business or something else that's the bulk of your business?
The bulk is semiconductor, clearly. The vast majority, and of our what we call electronics core, because we have put one part of our business, a surface solutions business, is for sale, and this has been already a signed deal, and it's being carved out. So of what we call electronics core, the rest is already 80% is facing the semiconductor industry, and only then 20% is left for the display industry.
Yeah, so you guys have a really wonderful overview of the semiconductor industry, right? Where is it growing? Is it growing everywhere? The famously TSMC and Intel are building big fabs in the United States. Where is it growing right now?
The semiconductor industry is probably one of the most fascinating industries. And if anyone has any problems with blood pressure, to work in a cyclical industry maybe is not a good advice. So it's going up and down. There's like, if you take my 35 years, if you take an average, it's like 4 good years, and then there will be 4 bad quarters. This is the typical cause of things. And it's always been like this. Now, meanwhile, it's getting a bit more complicated because different technologies have different cycles, and they're not fully in sync like they were in the past. And this is why at any given point in time, there are some businesses, of course, beautifully developing, and others are a bit more behind. In the current setup, of course, artificial intelligence drives a lot of growth in the semiconductor industry, and this is still predominantly focused on training large language models and the GPUs and the boards used in data center applications. This is driving a lot of growth as we speak, but other technologies are meanwhile catching up slowly as well. But it's not anymore like as nice of a wave that you could monitor. It's more like many waves on top of one another. So the industry is a bit more kind of spread out in terms of recovery than it was in the past.
That cyclical nature previously, was that tied to simply inventory piling up and then getting used and piling up, or was it tied to some other cycle in the economy?
If you look over a larger period of time, then predominantly it's driven by the fact that these fabs can run either fully utilized or they will be stopped. Lines will be stopped. And so there is no such thing as a 50% utilization typically, in a simplified way, just quite a simplified picture. So it means they run 100% and you create at some point inventory and you feel maybe now it's time to stop producing. I need to deplete my inventory, and then it goes comes all over again. That is the simplified picture. Of course, you can still find that in memory, where the products are a bit more commoditized. You find it less and less in logic, where the products are much more specialized on for different customers. So this is why the picture is not anymore as it was in the past. You know, the cycles in the early 2000s, where even the logic part, the CPUs for desktop computing were kind of almost commoditized, maybe the wrong word, but they were more replaceable than they are today. So in those times, it was piling up inventory and then depleting inventory again. This created the cycles. And it's still the situation that these fabs can run either kind of on a full utilization, or you better stop them because you're just burning cash.
Yeah, although given the advance of AI and the generative AI and the demand for GPUs and the shortage in GPUs, it seems that that inventory buildup is for the foreseeable future not going to be a problem. Is that right? That is a pretty steady demand.
Yeah, still bear in mind that AI is, in terms of percentage of all devices, semiconductor devices produced in the world, is still a fairly low percentage. We are still talking about a fraction of a percent. So that's why it doesn't really move the needle in terms of overall capacity and inventory yet. In terms of value, we're already reaching 10% of AI-related semiconductor devices, which of course includes not only the data center devices, it includes as well kind of edge AI devices like processors on a smartphone, processors for mobile computing at large. So this is the broader spectrum. 10% of the value equals somewhere 0.1, 0.2% of the devices manufactured.
How do you see that developing? Because certainly demand AI is going to spread. And are you guys, is that triggering any sort of shift in your production or triggering any sort of research for new materials that can be applied?
I think the first thing it does, the kind of the AI boom that we see, is it requires more sophisticated chips. That's what it does in the first place. So and more sophisticated by an order of magnitude, not just by a small margin. More complex architectures, smaller structure sizes, even what we call heterogeneously integrated semiconductor devices. It means you take chiplets and kind of glue them together in order to increase performance and packaging density. So that's, of course, again, a dimension that helps kind of accelerating our contribution to the industry. That's the first thing. The second thing is with the current AI boom is defined by by building capacity in data centers for training large language models. And then the current application is more you use a web interface, you do ChatGPT and use the large language model. What is still to come is edge AI. I mean, you put a AI chip on a smartphone, take the latest iPhone, you have that functionality on the iPhone already, but of course the percentage market share is not huge yet. And then you can do inference on the AI models right on your end device. You don't need to transfer data like crazy up and down the cloud. You can do that inference on your device. You mean things like Microsoft Copilot, for example, on a laptop computer can be done right on your laptop computer with kind of a CPU, GPU that you have in order to do the inference. That is the next level of AI use cases, and I think we will all see that coming. One could ask, what is the killer app? What will make that happen? We shall see. There's a lot being done around visualizing data, analyzing data. Text analysis, of course, is a big deal there as well. Picture editing is an important area as well. Kind of information research is an important part. I would suspect that a lot of these applications will be more and more compelling in their use case, that the demand for compute power, edge AI compute power on your end device will be increasing.
Yeah. So you see your business growing dramatically, I guess, in the next 10 years.
Yeah, we just upgraded our capital market guidance, midterm guidance based on those trends. Yes, I think we do have quite some confidence in the industry picking up on, driven by AI, the increased complexity of the chips, as well as the sheer volume over the next couple of years. Absolutely.
Yeah. And you guys develop new materials. Can you talk about what you're doing there? And obviously AI is being applied to material science and discovering new materials. Do you guys use AI in your research?
Great point. That's an amazing point. Of course, we enable AI and we use AI to enable us. So it's a kind of a full circle of things. So the way, of course, we need to identify new molecules, new precursors that are used for making chips requires typically a lot of experiments where you check whether this precursor does what it's supposed to do. Can you synthesize it? Is it stable enough? Does it have the properties that you need? And with AI, we can reduce the number of necessary experiments quite drastically. So in a recent talk, I have explained that kind of out of 100 different potential target molecules, we can remove 99 just based on AI and just synthesize one for the next level of testing. And then this next level of testing, that's another capability that we have built over the past 5 years. That we in the past we would have provided then this kind of synthesized molecule to a tool company or to a semiconductor fab in order to test the electrical properties. Meanwhile, we have the same capability within our own premises. It's called intermolecular. It's a facility that's based in the Silicon Valley in San Jose, and so we then can do electrical combinatorial testing of that material on a wafer in a transistor structure, and with that reduce the cycle of these refinements of our material drastically. In the past, we talked about 1 to 2 years, and now we are on a weeks scale. That's of course a huge benefit. Less experiments and faster cycle time is quite exciting. Of course, a pretty natural question that I typically get is then, do our chemists like that? Because if they do less experiments, do they lose their jobs? I think it's the opposite, because chemists, and I've talked to many of them, they like to do successful experiments. They don't like to do experiments that fail, and we remove the experiments that fail by artificial intelligence.
Yeah, and that pace of discovery, is that resulting in new products for you guys?
Absolutely. It is then identifying new material opportunities for our customers, which they then validate in their processes, which then feeds kind of novel technologies that is then implemented by our customers.
Yeah, I'm just curious. So when you synthesize a new molecule and you send it to California, in what form is that sent? Is that I don't know. Is it a vial of liquid? Is it a roll of sheet? Is it a block of solid material, or is it just a formula?
So it could be all of the above except the formula. So it could be a liquid, a gas, or a powder, a solid material, and it's shipped in, of course, containers, small containers that keep that intact and ensure safety for transportation. But it's the way how we handle these materials. Yeah, absolutely.
Yeah, and then when you validated it, you put it into production for semiconductor fabs. And how often do you come out with new materials for semiconductor fabrication?
Yeah, it's pretty tough to give you a kind of a precise number, because overall our product list probably has a couple of thousand different materials, material combinations, molecules, formulations, and it's quite a frequent event that a new process step requires a new formulation, a new precursor for our customers. So it's not just once a year. It happens quite frequently. Not everything will be then adapted for mass production, but still it's a pretty normal, if not daily, process.
Wow. And do you see the semiconductor fabrication process changing in the next 10 years? I mean, I don't know if it's been the focus, but from my point of view, from a journalist's point of view, the focus has been on smaller and smaller gate sizes, as you said, down to 2 nanometer. Is it going to continue miniaturizing, or are there gains to be had through other parts of the process, maybe through materials?
Yeah, that's a great point. So when I was at university at the end of the 80s of the last century, and already many people speculated, is Moore's law over? That was it's quite a while ago, and so maybe half jokingly we have said there's maybe like a derived Moore's law, that the number of people declaring Moore's law being over doubles every other year. So that's maybe I didn't get a trademark for that, so it's free to use. It's certainly not called Beckmann's law, I can tell you. But so the dimension, the focus was on what we call shrink. So getting lithography to create smaller structures, and everything else was auxiliary to making a semiconductor over a couple of decades, about 3 decades now. And of course, we are touching limits. There may be physical limits, but more importantly, there are economic limits to that, where it simply doesn't scale financially properly. And this is where then additional methods are being used. And probably the most novel way of doing it is the current trend, especially in the area of AI, around heterogeneous integration. So you build chiplets, and then you put these chiplets together in a certain way in order to better scale your performance on the chip. And with that, if you take NVIDIA's H1 Hopper, I think we're talking about more than 200 billion transistors, not on a single die, however, on this system, and you kind of almost glue stacks of memory very close to your GPU to reduce distances for data transfer, because data transfer is still the part of the whole compute with the highest energy consumption and the highest impact on latency. So that is then a system, I think specialists call that CoWoS. This is a chip on wafer on substrate, which is then the next level of densification of transistors, like 3 dimensions plus all these different capabilities to make even more complicated chips happen.
Yeah, and where do your materials come into play in that? In the glue or in the
thin film materials needed to build kind of the structures on the chip, in the planarization that kind of helps to create even layers, in the doping to kind of dope the kind of conducting layers, transistor parts of that. It is required as well as for patterning steps. It's required our tools for delivering the chemistry. It's required for our metrology instruments that help to measure the precision of the kind of the 3D stacking that is done for the integration. So everywhere, literally everywhere.
I have to ask because I've interviewed Andrew Feldman at Cerebras a couple of times, which is another strategy. Instead of chiplets, stacking chiplets, they're laying it all out on a wafer scale engine. Do you work with them as well?
We work in the early development with many different partners in order to identify new technologies. Of course, for us, the value is then in mass production with the big foundries. This is where the value is. But there's lots of different technologies in the early days on like wafer scale, as you explained, heterogeneous integration, which is already in mass production. And we talk about neuromorphic computing architecture that is maybe a bit further out, that bring compute and storage much closer together in order to like do the brain-like way of computing data. And of course, far out things like quantum computing. We work with PsiQuantum in the Silicon Valley as well in identifying materials for qubits in future. So there's things that are near term and things that are really far out, and we try to cover in a meaningful way different phases of the life cycle. But the focus, of course, is on what is very close to mass production and helps our customers to scale today's technologies.
So you guys are sort of the hidden hand behind a lot of semiconductor manufacturing or semiconductor development. How large is your organization, and yeah, I mean, how many chemists and engineers do you have working for you?
And we have put ourselves like under a slogan that we have used for a couple of years, that we are kind of the company behind the companies advancing digital living, that has like really encouraged the team to do what it does. So we take pride of making our customers successful. So if we feel there's something great coming out of our customers' pipeline and we were an integral part of making that happen, I think it creates a lot of pride in the organization. Overall, our company is more than 62,000 people globally. The electronics sector is in 7,000 people, and overall, our company employs in all kinds of R&D and R&D related functions more than 6,000 people, 6,000 R&D researchers. Driving science and technology across different domains, from chemistry, biology, physics, engineering, computer science, data science as well. So highly science-based company ever since its foundation more than 350 years ago.
Yeah, and where are your biggest markets?
That is basically where our customers are. So in the current environment, there is a lot in Asian countries, South Korea, Japan, in regions like Taiwan. In of course, United States is amongst our largest geographies. Europe in the electronics industry is a bit lagging behind. I see that with quite some sadness as a European citizen, and we try to catch up. However, we do have great research centers over here, such as IMEC, such as LEDI, and very important research centers for the global semiconductor industry. So we are basically where our customers are.
Yeah, and the semiconductor industry in Europe, are there fabs being built right now?
We do have already a number of highly specialized fabs in Europe, of companies like Infineon, like STMicro, like NXP, and of course fabs operated by companies like Global Foundries, like Intel, of course, in Ireland as well. And I've just visited in summer kind of the groundbreaking of the so-called ESMC fab, which is a joint venture between companies like TSMC, NXP, Infineon, and Bosch.
Is there anything I haven't touched on that you want to say?
I think if I have kind of left the understanding that materials are now kind of the new dimension of driving performance of semiconductor devices, then probably I've done a good enough job. So some of our customers call it, meanwhile, this is the age of materials, coming from the age of tools, the age of kind of lithography, now turning into the age of material to make these amazing devices happen. I think it's a very important part. Second is AI. So we use AI and we enable AI. At the same time, it's an important part of driving value, and kind of all across different domains that we cover. I think I've tried to explain how the technology overall kind of emerges into new fields, heterogeneous integration as probably the most important new dimension, 3D structures. We talk about memory anyway being in a 3D structure. Meanwhile, logic is more and more turning into 3D transistors. Probably there will be 3D logic eventually at some point. So there's many different areas that give us kind of reason to be optimistic about how technology evolves and how the market opportunity evolves going forward.
Yeah, well, actually, and that brought up another question. In stacking or in, I mean, that was Cerebris's thesis, is that you etch a wafer and then you cut it up into little chips, and then you wire all these chips together, and it's those connections between the chips that determine latency, because or contribute to latency, because there's a limit to how quickly they can transfer data from high performance, high bandwidth memory to the logic, for example. And it seems like that connection, that the limit on that data transfer would be a materials science problem. Are you guys working on that at all?
I think the stacking is one dimension. I think the first step, of course, if we can, we try to have 3D structures on one wafer. This is always the more efficient part, like in 3D NAND in storage. There's just layer on layer on layer up to 300, if not more, that are used to store data in NAND structures. This is one part. And this will be explored for DRAM as well. It will be explored for logic. This is a bit further out. If that doesn't work, then of course the next opportunity could be you stack dies, like you just said. You kind of produce a die, and then you stack these dies, and of course the latency is defined still by distance, and the distance between distance on a wafer to distance across wafers is orders of magnitude, and this is where, of course, latency and energy consumption comes from. This is where we then look into leakage current, for example, conducting structures. So this is where materials properties can help to improve that. If you take that example in a very simplified way, and I try to make it a simple example, the conducting lines that are created on a chip, they used to be, when I was at university, as I said, aluminum was a material of choice. Then we saw over time, again, I simplified in one use case, over time copper was then used as well for all these power distribution, still used for kind of backside power distribution or layers on top of the transistors. Then underneath, for smaller structures, you use tungsten as an important material. But as you go forward, you see limits coming up in terms of the electrical properties, and this is where we now explore molybdenum is the kind of the new kid on the block, because it performs better than the traditional materials in that spectrum. It shows how material innovation helps to solve problems created then by higher densification on a chip. Leakage current is one dimension, very important. Then, of course, conductivity overall, very important to make high performance chips possible. And then in stacking, you have that, of course, in the third dimension with how do you build these contacts, how you do this through silicon vias, which is the holes that you drill in order to build contacts to your kind of transistor layers or storage layers on a chip, and how you package it all together to make it sturdy enough, create performance and improve energy consumption. I hope that makes sense. A very simplified paper to tell you how the innovation cycles over even a longer period of time take place.
And I would guess then you're continuing to look for new conducting materials for those connections.
Absolutely. This is where the kind of the 80% and the remaining 20% of the periodic table of elements comes from, by exploring can other materials have better properties in what we try to accomplish on a chip. This is exactly where that comes from. Of course, with all questions on cost of making a chip, stability, and all different factors that are kind of required to be observed.
This has been fascinating because it opens up understanding of another dimension in semiconductors. And you guys are a public company?
We are 70% held by the founder's family, who is now in the 13th generation, holding 70% of our equity, and 30% is publicly traded. We are listed on the German DAX index. And so this gives us, as we call it, the best of both worlds. So the stability, longevity of a family-owned company with a high involvement of our owner's family, as well as transparency and the agility of a publicly listed company. So we have kind of best of both worlds.
What does the future hold for business? Ask 9 experts and get 10 answers. Bull market, bear market, rates rising or falling, inflation going up or down. Can somebody please invent a crystal ball? Until then, over 40,000 enterprises have future-proofed their business with NetSuite by Oracle, the #1 cloud ERP, bringing accounting, financial management, inventory, HR into one fluid platform. With one unified business management suite, there's one source of truth, giving you the visibility and control you need to make quick decisions. With real-time insights and forecasting, you're peering into the future with actionable data. If I were a larger organization, this is the product I'd use. Whether your company is earning millions or even hundreds of millions, NetSuite helps you respond to immediate challenges and seize your biggest opportunities. Speaking of opportunities, download the CFO's Guide to AI and Machine Learning at netsuite.com/ionai. That's NetSuite, netsuite.com/ionai, EYEONAI, all run together. to get the CFO's Guide to AI and Machine Learning. The guide is free to you at netsuite.com/ionai. netsuite.com/ionai.